Hi everyone. I'm just addressing your feedback as usual. I'm still unsure of the meanings of quantum numbers and how they play a role in electron configurations. So, quantum numbers themselves, like the idea of a quantum number, is just that according to quantum mechanics, things exist in discrete states. You either are here or you are there. You have this amount of energy or that amount of energy. Can be multiple possible configurations, but the idea is they exist in those discrete configurations. So an analogy I normally like to draw is with a coin versus a... Okay, so imagine you have a coin. So a coin has two possible sides that you could view. You can either view it heads up or you could view it tails up. Those are two possible states of being. If you have I don't have any dice with me, but if you had a die, you could roll the die, and when it rolls up, it's in one of 6 possible configurations, and you could assign a number to each of those. Now imagine you have a ball. When you roll the ball, there's an infinite number of sides that it could land on. It has a continuum. In quantum mechanics asserts that reality is more like a coin or a die than a ball, in the sense that there's only certain discrete sides that you can land on. And the quantum numbers essentially label or distinguish those different possible options. So for an electron in a hydrogen atom, it can exist in different orbitals. Those different orbitals are sort of like the different states, the different sides of the coin, or the different sides of the dice. And we use quantum numbers to distinguish those different possible configurations. Now, what does that have to do with electron configurations? That basically is where we apply the Pauli exclusion principle. So the Pauli exclusion principle basically states that if you have 2 electrons in an atom, they have to have different quantum numbers. They have to have different quantum numbers. We describe the state of a system or the configuration of an electron in a system by its wave function or by its orbital. So we distinguish that by 3 different quantum numbers to describe the orbital. And then we have a 4th quantum number which describes the spin state of the electron. Basically, electrons can either be heads up or tails up. They have 2 different options to describe their sort of internal motion, their internal characteristics, and then we have 3 different quantum numbers to describe the motion of the electron around the nucleus. The 4th quantum number basically, to some extent, describes an electron's internal motion. We call it spin because we like to think of the idea of the electron spinning, that it has a charge and it creates a magnetic field. We don't really, when I say we, meaning physicists, don't really picture the electron as spinning. It's a point particle. It doesn't actually have any internal structure. It's not like a little ball that can spin around, but it manifests behavior as though it were spinning. So we say it can be in 2 possible spin states. Now, what does that have to do with electron configurations? Again, the Pauli exclusion principle tells us that electrons have to have different quantum numbers. Or in essence, we can only fit electrons into different orbitals. We try to fit electrons into different orbitals because they want to have different quantum numbers. But because there's a last quantum number and there's 2 different options, either spin up or spin down, because of that we can essentially fit 2 electrons into each orbital. So let me run you through this. So if I had the 2p orbitals, the 2p orbitals correspond to n equals to 2, L equals 1, which means m sub L can be -1, 0, or 1. So there are three possible different orbitals. Ooh, I really need a better marker than this. Is this one going to be better? Yeah, that's better. So there are 3 possible p orbitals, 2p orbitals. There's the 2px, the 2py, and the 2pz. So this one, its set of quantum numbers would be 2, 1, and say -1. That's one set of quantum numbers. This guy has 2, 1. Again, it's 2, 1 because it's a 2p orbital, so the 2 refers to the 2. The 1 refers to the fact that it's in a p orbital, and then it can have 0 for its magnetic quantum number. And then this guy can be 2, 1, or +1. So that would be the third orbital. And then within each of these orbitals, an electron has 2 other options. So you could have one that's either spin up, that's for the 4th magnetic quantum number. M sub s can only have the values +1/2 or -1/2. The numbers themselves, the actual values of the numbers, are not that important. What's more important are the rules for those numbers, how many different values they can take. And so the spin quantum number can only have 2 possible values, spin up or spin down. So within this orbital, I can have one that's spin up that has a +1/2 quantum magnetic quantum number, and I can have one that's spin down that has a -1/2 quantum number. So there could be 2 electrons that can have the same principal quantum number, the same angular quantum number, and the same magnetic quantum number, but they have to have different spin quantum numbers. So that's essentially how quantum numbers play a role in determining electron configurations, in the sense that there are certain rules for predicting possible electron configurations. One of the most important rules is the Pauli exclusion principle, and that's the one that most directly relates to quantum numbers. I'm still confused about writing out orbitals. Can you explain how they get filled? Why is it a 2p6 and not 2p9? So why... So again, the reason why, the way you fill up orbitals is by applying the Aufbau principle, filling up the orbitals in order of energy. Your general guiding principle is you always want to find the lowest energy configuration, no matter what that is. It's not always, there are a bunch of caveats that we throw in that we'll end up teaching to you and throwing at you, and all those caveats somehow relate to finding lowest possible energies. So for example, let me give you an example here. So I guess I can do, let me do neon as an example here. So neon should have, let me think about this, 10 electrons. Yeah, I think it has 10 electrons for neon. So the way the orbitals get filled up is 1s, 2s, then the 2px, 2py's. There's 10 of them, so you fill them up by applying the Aufbau principle. The Aufbau principle says fill up the orbitals in order of increasing energy. So I can put 2 of them into the 1s orbital. Again, the idea is each of these different arrows represents the different spin configurations. So these guys have the same principal quantum number, the same magnetic angular quantum number, and they have the same magnetic quantum number. So in this case, it's 1, 0, and 0. That describes this orbital, and within that orbital, the electrons have 2 other options. They can be +1/2 or -1/2. We're still going to fill up all these orbitals in order. So I have 2 of them in the 1s, 3, 4 of them in the 2s, and then 5, 6, 7, 8, 9, and 10 for neon. So I applied the Aufbau principle, I've applied Hund's rule, where I half fill the orbitals before completely filling them. And then the question is, why is it 2p6 and not 2p9? Well, there are only 3 2p orbitals, and each p orbital can fit 2 electrons, because again, there are 2 possible options for your spin state within a single orbital. A single orbital is determined by the first 3 quantum numbers, and then within that orbital you still have 2 other options left for the spin quantum number. So that's why it has to be 2p6, because you can only fill up 3 of those orbitals with 2 electrons each, so 6 electrons total, not 2p9. You couldn't do 2p9, there's just not enough space available for you, or there's no extra options. The Pauli exclusion principle tells you that there have to be different quantum numbers for every electron. So if I try putting, say, another electron into one of these orbitals, now this electron has the same principal quantum number, the same angular quantum number, the same magnetic quantum number, and then these 2 guys would have the same spin quantum number, because they're both spin up. Sorry, I sometimes have a tendency to write them like with half arrows, just because it's a little faster, but they really should be, it doesn't really matter. They can be full arrows, they can be half arrows, it doesn't matter. But if I did something like this, these 2 electrons would have the same principal quantum number. Sorry, they would have the same exact set of quantum numbers, and that would violate the Pauli exclusion principle. Essentially, they would be occupying the exact same space at the exact same time, and they would be completely identical towards each other. And you wouldn't be able to tell them apart, and that would mathematically, that causes the wave function to take to have a 0 value. So mathematically, they would essentially cancel each other out, and the 2 electrons would cease to exist. So the Pauli exclusion principle is a rule of thumb to prevent that from happening. Next question, orbitals. Is this an orbital? Or is this an orbital? Is the orbital all 3 of these, or is it just one of these? An orbital is referring to basically one of these horizontal lines. When I draw out my little energy level diagram, I use a horizontal line to represent the energy of a single orbital. So each of these represents a different and distinct orbital. So I would say this is one orbital. The 3 together represent a subshell. And specifically, it's the 2p subshell. Remember, we said that electrons and orbitals are sort of grouped into shells. The shell number is determined by the principal quantum number. So I would say that the 2s and these 3 2p orbitals, all of them are in the same shell. Again, they're in the second shell, and n equals 2. This is the 2s subshell. So that's a subshell, and then this is a subshell, referring to the different angular quantum numbers. They have the same, they're all 2p orbitals, so they're in the 2p subshell. These electrons are in the 2s orbital, they are in the 2s subshell. So again, that's just yet another way to sort of group together orbitals into shells and into subshells. Okay, so those were all the questions that I got on today's topic. I will be posting the next set of reading assignments and homework assignments later this evening, or possibly early next morning. I'll try to get at least at least the reading assignments posted tonight. Homework assignments, I don't want to just throw anything in there. I like to take a little bit of time crafting them, so I might end up posting that tomorrow morning, but I will try to get those posted as soon as possible for people so they can get started on them. If you have any further questions, please shoot me an email. I'd be happy to answer any concerns you have, and if not, I will see everybody on Monday. Have a good weekend, everyone.